Hello, science fans! Are you ready to dive into a subject that's all around us all the time? The air we breathe, the water we drink, and even the juice in our juice boxes. We're talking about fluid mechanics. Now, that might sound like a super complicated high-tech term reserved for rocket scientists and engineers in white lab coats, but I promise you it's something you already know a lot about. It's the science of stuff that flows. Today we're going on an adventure. We're going to unlock the secrets of liquids and gases, how they push, pull, lift, and squeeze. From the deepest parts of the ocean to the highest reaches of the sky, the rules of fluid mechanics are at play. Understanding these rules isn't just for passing a science test, it's for understanding the world. It helps us figure out how giant steel ships can float on water and how massive airplanes can soar through the air. So, first things first, what in the world is a fluid? When you hear that word, you probably think of water, right? And you're not wrong. Water is a fantastic example of a fluid. A fluid is any substance that can flow and change its shape to fit the container it's in. This includes all liquids like water, oil, honey, milk. If you pour it, it flows. It doesn't have a fixed shape of its own. But wait, there's more. Liquids are only half of the story. Gases are fluids too. Think about the air all around us. We can't usually see it, but it's there, and it's definitely a fluid. It flows, it moves, and it fills up any space it's in, whether that's a balloon, a tire, or the entire room you're sitting in right now. So, when scientists talk about fluid mechanics, they're talking about the science of both liquids and gases. Now let's talk about a super important property of every fluid: density. It sounds like a complex word, but the idea is pretty simple. Density is just a measure of how much stuff is packed into a certain amount of space. Let's think about some liquids. Imagine you have a cup of water. Imagine you have a cup of honey. They take up the same amount of space, but the honey feels heavier. That's because honey is denser than water. This is why some things float in water while others sink. Less dense than water, floats. Denser than water, sinks. Density isn't just for liquids, it's for gases too. Hot air is less dense than cold air. Heat makes air molecules move faster. The molecules spread farther apart, so density goes down. That's why hot air balloons float. Let's move on to another big idea: pressure. You've probably felt it before. When you dive to the bottom of a swimming pool, you can feel the water pushing on your ears. That push is fluid pressure. Pressure is the amount of force a fluid pushes on an area. Imagine fluids are trillions of tiny molecules bouncing around. When these molecules bump into a surface like your eardrum or the sides of a container, the combined effect of all those tiny pushes is pressure. Fluid pressure pushes in all directions at once. It doesn't just push down from the top, or up from the bottom, all sides simultaneously. That's why submarines must be built incredibly strong. Water pressure tries to crush them from every direction. Think about our atmosphere. We're living at the bottom of a huge ocean of air. All that air above has weight and pushes down on us. This is atmospheric pressure. We don't feel it because our bodies push outward equally. Now let's meet a brilliant thinker named Blaise Pascal. He figured out something amazing about fluid pressure that we now call Pascal's principle. It sounds fancy, but the idea is quite simple and, honestly, incredibly powerful. Pascal's principle states that when you apply pressure to a fluid that's in a closed container, that pressure is transmitted equally to every single part of the fluid and to the walls of the container. This principle is actually the secret behind one of the most useful inventions ever: the hydraulic system. Hydraulics use this idea to multiply force. A small force applied to a small piston creates a certain pressure. That same pressure acting on a large piston with its much bigger area creates a much larger force. You see this magic at work every day? When a mechanic at a garage lifts a heavy car with what looks like a simple pump, they're using a hydraulic lift. Their small push on a pedal creates pressure in a fluid, usually oil, and that pressure is transmitted to a large piston under the car, generating enough force to lift thousands of pounds. Okay, let's travel back in time to ancient Greece to meet another science superstar, Archimedes. So, the story goes that he was given the tricky job of figuring out if a king's crown was made of pure gold, but he couldn't damage it at all. While thinking about this problem, he stepped into his bathtub and noticed the water level rise. In a flash of insight, he realized that the volume of water that spilled over was exactly equal to the volume of his body that was submerged. He was so excited that he supposedly ran through the streets, shouting "Eureka!" This discovery is now known as Archimedes' principle. It states that any object that is partially or fully submerged in a fluid is pushed upward by a force equal to the weight of the fluid that the object displaces. Let's make that a little simpler. When you put something in water, it has to push some water out of the way to make room for itself. The water pushes back. This upward push is called the buoyant force. This principle leads directly to the law of flotation. This law tells us why some things float and others sink. It's a battle between two forces: the object's own weight pulling it down, which is gravity, and the buoyant force pushing it up. Think about a beach ball. It's really light for its size. When you push it into the water, it displaces a lot of water. The weight of that displaced water is quite large, creating a strong buoyant force. This buoyant force is much greater than the beach ball's own weight, so the ball pops right back up to the surface. Archimedes' principle isn't just a cool idea explaining why beach balls float. It's actually a cornerstone of engineering, and it has massive real-world applications. Shipbuilding is the most obvious example. How can a gigantic ship made of thousands of tons of steel float? The secret is the ship's shape. A ship isn't a solid block of steel, it's built with a huge hollow hull. That shape displaces an enormous volume of water. The buoyant force from that displaced water supports the weight of the ship, its cargo, and its crew. The same principle lets submarines dive and surface. Submarines have special ballast tanks. To dive, water floods into the tanks. That extra water increases weight so the submarine sinks. To surface, pumps force the water out and replace it with compressed air. The sub becomes lighter than the buoyant force and rises. Buoyancy works in air too. Air is a fluid. A blimp or zeppelin floats for the same reason a ship does. They're filled with a gas less dense than air, like helium. Because they're large, they displace a huge volume of air. The displaced air's weight exceeds the blimp's total weight. Even a life jacket uses Archimedes' principle to save lives. Life jackets are low density and trap air. They add volume without much weight. That displaces more water and increases buoyant force. The upward push keeps your head above water. Now let's fast forward a few centuries and meet Daniel Bernoulli. He was part of a famous family of mathematicians and scientists, and he gave us another incredibly important idea about how fluids behave, but this time it's about fluids in motion. Bernoulli's principle is a little bit like magic, but honestly it's pure science. In its simplest form, Bernoulli's principle states that for a moving fluid, where the speed of the fluid increases, the pressure within the fluid decreases. Imagine water flowing through a pipe. If the pipe suddenly gets narrower, the water has to speed up to get the same amount through. It's kind of like when you put your thumb over the end of a garden hose. The water speeds up and sprays out faster. In that narrow, fast-moving section of the pipe, the pressure pushing against the sides is lower than in the wider sections. Faster speed, lower pressure; slower speed, higher pressure. They are inversely related. You can see this principle at work with a simple experiment. Take 2 empty soda cans and place them on a table a couple of inches apart. Now blow a stream of air directly between the 2 cans. What do you think will happen? Most people guess the cans will be blown apart, but try it. You'll see that the cans actually move toward each other. Why? Because the air you blew between them was moving very fast, creating a region of low pressure. The stiller air on the outside of the cans has a higher pressure, and this higher pressure pushes the cans inward toward the low pressure zone. Bernoulli's principle isn't just for lab experiments. It's actually the science behind some of the most spectacular feats in sports and technology. Let's start with an airplane. How does a massive metal tube with wings stay in the sky? The secret is the shape of the wing, the airfoil. An airplane wing is curved on the top and flatter on the bottom. As the plane moves forward, air splits to go over and under the wing. The curved top gives air a longer path to travel, so the air on top moves faster than the air beneath. Now apply Bernoulli's principle. Faster air on top creates lower pressure. Slower air beneath creates higher pressure. High pressure below and low pressure above produce a net upward force. We call that force lift. When lift exceeds the plane's weight, the plane takes off. The same principle explains the mesmerizing curve of a baseball and the swerve of a soccer ball. A pitcher throws a curveball with lots of spin. The spinning ball drags a thin layer of air with it. On one side, the dragged air moves with the flow. Airspeed increases. On the other side, it moves against the flow. Airspeed decreases. That speed difference makes low pressure on the fast side and high pressure on the slow side, which pushes the ball and makes it curve. You can even see Bernoulli's principle in everyday items. A perfume atomizer and a paint sprayer force a jet of air to move quickly over the top of a small tube dipping into liquid. The fast air creates low pressure above the tube. Normal atmospheric pressure on the liquid surface pushes the liquid up the tube and into the airstream where it breaks into a fine mist. From the flight of a jumbo jet to the simple act of spraying perfume, Bernoulli's principle shapes our world. For more science lessons and free resources, check out WANA Educational Services. They have great materials to explore the wonders of science. Teacher Cato Ivan brings lessons on a daily basis. Catch up with Teacher Ivan on WANA Educational Services e-learning platforms such as YouTube, Instagram, Facebook, TikTok, and X. Science is a way of thinking, a way of looking at the world with curiosity and asking why. Fluid mechanics reveals incredible hidden connections. The same rule that makes a baseball curve also helps a 747 fly. Understanding these principles gives you new eyes to see the universe's intricate design. So keep asking questions, keep experimenting, and never stop exploring. The world is your laboratory. Don't forget to check on WANA Educational Services e-learning platforms, where quality learning matters. Consider it.